Hey there guys, welcome to Unit 10 Note C. Today we're going to talk about LeChatlier's principle, which is all about finding a balance. So we're going to look at three different factors that are going to actually affect the equilibrium concentrations, or the ratio of product to reactant that exists at an equilibrium, things that can shift that equilibrium. So the idea is that equilibrium is stable. A system will stay at equilibrium as long as it can, but if some outside effect acts on that system, then the equilibrium can shift. We would call this changing the condition. We're going to change our equilibrium, and the principle behind how that changes is called LeChatlier's principle. So LeChatlier's principle basically says that the reaction is going to try to undo the effect of any stress. Whenever there's a disturbance in the system, LeChatlier's principle says the system will counteract that specific disturbance in any way. So let me give you a non-chemistry demo for a second. Say my ruler or yardstick here is at equilibrium. If I stress out the system by pushing down on this side, LeChatlier's principle says the system will counteract that exact effect. So if me pushing down on this side, the system will then push up on that side. Yeah, there's other effects going on in the system, but LeChatlier's principle focuses specifically on undoing the stress that was caused. So it'll tell you in the problems what the stressor was, and you have to say how to fix it. So we're looking at the effect caused by the stress for LeChatlier's principle. So let's look at our first factor, which will be concentration. So if the stress is adding more of a reactant or more of a product, the system will act to consume that added substance. However, if the stress is removing that substance, then LeChatlier's principle says the system will react to replace it. So if something is added, we'll use it up. If something is removed, we're going to replace it. We're going to try to negate the effect of the stress. So let's look at a specific example. Say I have hydrogen and iodine gas in equilibrium with this hydroiodic acid. So at equilibrium, we would say all is equal or level. The question is, what would happen if we added some extra H2? So here the system's happy at equilibrium, but now we've stressed it out by adding more of our reactant. The fix will be to use up that extra H2. We want to remove it. So then the question is, which reaction would use up the H2? Would the forward reaction use the H2, or would the reverse reaction use the H2? Well, the forward reaction would use up the H2. The reverse reaction would replace it. We're trying to use it up. So that means the reaction would actually shift to the right, favoring the forward reaction to use up that H2. And then the side effect is that we're going to form more of the HI. So you're going to see an increase in the product concentration as you're using up the extra H2. The I2 would need to be used up also to form product, right? So you're going to see a decrease in these concentrations. These are the side effects I was talking about. LeChatlier is focused specifically on what's the shift. So in order to use up the extra H2, we're shifting to the right. Now, what if instead we had removed H2? So let's go back to our equilibrium where everything is balanced, and now the stress is removing some of the reactant. Well, the system will act to replace it. So which reaction would be making more H2? That would be our reverse reaction, shifting us to the left in order to replace the H2. The side effects would be also making more making more I and then using up the HI, because that's what happens in that reverse reaction. So we're trying to look at what shift, which direction we need to do directly to undo the stress. The second factor that can affect equilibrium is temperature. The good thing about temperature is we have learned how to take heat energy and actually put it into a reaction. We can actually treat heat as a reactant or a product. Even if it's given as delta H, you know, the negative delta H's would be on the product side and the positive delta H's would be on the reactant side. So we can just put them right into the equation and treat them actually just like concentration. Just think of it as changing the concentration of heat energy. So let's look at one. Here we have a reaction with the energy on the product side. So this would be an exothermic reaction, meaning it's producing energy. So what would happen if we increase the temperature? Well, if I was at equilibrium and my heat was on the product side An increase in temperature would mimic increasing the concentration of products. So what's going to allow me to use up those products and get that back down to normal? Well, that's going to be my to use up the products, sorry. Easy to go backwards on this stuff, right? If we're increasing the temperature, that's the stress. I want to use it up. It's actually the reverse reaction. In order for this to go back to where it started, we would need to be using it up. So that would be our reverse reaction, shifting to the left, favoring the reactants. Let's think a little more deliberately about what happens to all of our reactants and product concentrations this time. So if I'm favoring left, if I'm favoring my reactants, I'd be making more O2 and SO2, and in turn using up the SO3, because the goal was to use up the heat and get that back down to baseline. So the side effects would be decreasing the SO3 and increasing the SO2 and the O2. This is important because when you change the temperature, you're also going to change the equilibrium expression. So our new Kc value, we need to determine if it's higher or lower. So you remember the Kc was product over reactant. And although we don't have to go through all the math to actually calculate Kc, we do need to be able to predict whether that would increase or decrease. So the product was the SO3, and we can see that that would be decreasing, whereas the reactants would both be increasing. So what would happen to the K value then if you're now taking a smaller number and dividing it by a bigger number, or taking a smaller pizza and cutting it up into more pieces? You would get a smaller piece. Your K value would decrease. So based on the shift to the left, you're going to get a lower K value. Now let's look at what if I, instead of increasing the temperature, decrease the temperature. So with a decrease in temperature, let's reset our equilibrium here. And now the stress is that I've dropped my heat energy. Well, what's going to replace that heat energy or make more heat energy? That would be our forward reaction. So the shift will be to the right, making more product. So in order to get this back to baseline, I'm going to be shifting to the right to make more of that, which also means that, side effect here, I would be using up more of my SO2 and O2. And that in turn is going to change my K value. So K again is product over reactant, where the product in this case is increasing and decreasing my reactants. So what happens to K if you have a bigger number divided by a smaller number, or a bigger pizza cut into less pieces? Well, your piece would be bigger. Your K value would increase. So when you have a shift to the right, you're increasing your K value. You're increasing your ratio of product to reactant. All right. So with K, you have to be careful when you change, the temperature. I have the right button here. So this is a reminder that K changes when temperature changes, but the good thing is it only changes when temperature changes. So you don't have to worry about new ratios when you're changing concentrations of reactants or products, or our next factor, which is going to be pressure. You don't have to worry about different K values. You only have to worry about different K values for temperature. All right, speaking of pressure, let's look at a change in pressure. So if you increase the pressure, you're going to favor the reaction that has fewer moles of gas. Increasing the pressure essentially has kind of a squishing effect. Increasing pressure, less moles. Whereas if we have a lower pressure, we would then favor having more moles. And this is an effect of the second law of thermodynamics. Nature loves chaos, right? The more chaotic, the better. So if I'm under no stress, or if I'm at low pressure, then I'm going to favor more moles. That has a better entropy. So basically, we want to look at the number of moles and pick the side based on whatever the change in pressure is. The big catch here is that it only matters for moles of gas. Only gases are compressible. Only gases have indefinite volumes. And so only moles of gas need to be considered when you're looking at change in pressure. So let's look at some questions. So first thing I want to do is look at this equation and figure out how many moles of gas I have on each side so that I can answer the questions. So on the left-hand side here, I have a 2 in front of a substance, and I verify, yes, it is a gas. That's the only reactant on this side, so I have 2 moles of gas on the left. If I had multiple substances, maybe 2 reactants, if they're both a gas, you would add up the number of moles. If only one of them is a gas, you would only use that number for the number of moles of gas. On the right-hand side, I can see my coefficient is 1, and I verify that it is a gas, so I only have 1 mole of gas on the product side. So which is it that I want if I'm increasing the pressure? An increased pressure would favor the side with less moles, which would be my product side. So that means I'm going to favor the reaction that favors the product, which would be the forward reaction. And so it would shift to the right, making more product, making more of the stuff that has 1 mole. Now if I decrease the pressure at a lower pressure, I want the part that has more moles. So I would favor the side that has 2 moles over the side that only has 1 mole. So that reaction favored would then be the reverse reaction, or a shift to the left. So that's going to form more reactant. All right, so let's put all this to the test here. I've got one balanced equation up top with heat energy in it already for you. And I want you to consider the changes for temperature, pressure, and some different concentrations. Determine whether you think the shift would be left or right for each of these changes. All right, let's look through them one at a time. So first, if I'm increasing the temperature, that would be like increasing the concentration of the product. It would be the reverse reaction, or a shift to the left, that would use that up. Whereas if I'm decreasing the temperature, I would need to replace it, or shift to the right. If I'm increasing the pressure, I would want the part with less moles. Remember, increased pressure wants less moles, where decreased pressure wants more moles. So how many moles do we have? On the left side, they are both gases, so I'm going to add 1 plus 3 for a total of 4 moles. And compare that on the right, I have gas, that's not a gas, so I only have 2 moles on the right-hand side. So where I'm increasing the pressure, I would want the one on the right-hand side. I would shift towards the right, whereas if I want less moles, because I'm at a lower pressure, I would shift back to the left. Always favoring the number of moles opposite the increase or decrease in pressure. All right, let's look at adding some H2, which is one of our reactants. So what happens if the stress is that there are more reactants? Well, then we would want to use those up and therefore shift to the right. Removing NH3, removing the product. Well, then I want to replace the product. So again, that's actually also going to be a shift to the right. So notice that the shift to the right can be caused either by adding extra reactant or removing some product. Either one of these things is going to cause the reaction to want to move forward more. Now the last one, adding a catalyst. Do we think that adding a catalyst will cause a shift to the left or the right? Well, I didn't talk about catalyst as one of the factors, right? So it would actually not have an effect on the equilibrium position. Only pressure for gases, temperature, and concentration affect equilibrium. There are 6 factors that affect reaction rates, but only these 3 affect equilibrium ratios. So this is going to be our a factor that doesn't affect it at all, and so you're going to see no change in equilibrium, which kind of makes sense because catalysts were not consumed in the reaction. They're not going to actually affect your equilibrium status. All right, let's look at just a couple more examples, starting with some on pressure. So with pressure, we want to consider the number of moles. So let's determine that first for this reaction. On the left-hand side, first thing I want to do is make sure that they're all gases, and they are this time. So I have 4 plus 5 is 9 moles. And I have, again, all gases. So 4 plus 6 would be 10 moles. If I'm increasing the pressure, then I want less moles. So which side has less moles? my reactants, and so I'm going to want that reverse reaction. I'm going to shift to the left. Let's look at another one. Here again, I want to go through and make sure I'm only looking at the gases, and again, they're all gases. So on the left, I have 2 plus 1, so 3 moles, and on the right, I only have 2 moles. So if again, I'm increasing the pressure, then I would want the side with less moles. So this case, that would be the product side. So I would shift to the right. So you're always looking at relating the increase in the pressure to less moles or decrease in the pressure to more moles. All right, let's look at changes in temperature now. So I get asked a lot. So if it's exothermic, is it always right? Or if it's endothermic, is it always left? There is no good answer to that. You have to evaluate each question individually. So I'm going to look at some exothermic and some endothermic here. First one, where I'm increasing the temperature, basically means I'm going to be treating that side of the equation as if I'm increasing it. So if I'm at equilibrium and looking at an exothermic reaction where the heat is a product, if I increase the temperature, then in order to remove that extra heat, I would need to use it up, which is going to be our reverse reaction. So if I'm favoring the reverse reaction, that would be a shift to the left. A lot of times they'll give that to you as actual numbers instead of just saying generically heat. Treat it the same way. So in this case again, because the stress is extra product, I would want to use that up with a shift to the left. Now let's look at one where the heat is on the reactant side. So this would be our endothermic reaction. If I have an endothermic reaction and I increase the temperature, it would be like increasing a reactant instead of a product. So how do I use up my reactants? That would be a forward reaction. So in this case, you would get a shift to the right. So you do have to consider which side the heat is on before you jump to the conclusion of which way it's going to shift. All right, so let's kind of sum this up a little bit. In order to solve LeChatlier problems, the first thing that you have to determine is how to undo the stress. How do we get the stress removed or undo the effect? So the problems will give you an effect, give you a problem, and you have to undo it. So for concentration, if something was removed, you want to replace it. And if something was added, you want to remove it. So you're basically going towards things that were removed and away from things that were added in order to use them up or replace them. Heat works exactly the same way if you think of it as a reactant or a product. If we put it into the correct side of the equation, we can think of that heat then being increased with increased temperature or decreased with decreased temperature. Treat it the same way as concentration. With pressure, though, you can't really think of it the same way. Pressure is a little bit different. You have to make sure, first of all, that you're only looking at moles of gas, and then you have to apply the second law of thermodynamics. So at a lower pressure, I would want more moles of gas, and at a higher pressure, you can have that squishing effect to get less moles of gas. Once you figure out which direction you're going, then you can figure out what's happening because of that shift. But that right there is going to tell you whether you're going left or right. And then if you are going right, that means it's going to be the forward reaction favoring more product. You're going to see increased concentration of product and increased K values. Whereas if you're going to the left, you're favoring the reverse reaction, making more reactants, and that's going to lower your K value. All right, I hope this helps kind of summarize everything with LeChatlier problems. My best advice is to try to focus on the effects and don't let the initial stressors confuse you. Focus on what you have to do to fix those stressors. All right, guys, that's going to do it for Unit 10. Our next unit is Unit 11 on acids and bases. We'll see you there.